Hello everyone, now I want to discuss about a very important part of this unit is we're looking into the properties now, and based on periodic law the properties actually for those elements repeat itself on a regular basis. And now we're looking into the families or the groups. As we indicated on this modern periodic table, we're looking into the properties of the elements in the same family or groups, the vertical column, and compare them and trying to identify the patterns. Also, we're going to compare the property across the periodic table in the same rows. We call it periods. Also want to see seeking the patterns. The first property I want to address is the atomic radius. So actually, what is the atomic radius and how actually we can measure the atomic radius? That turns out to be a rather complicated problem, and here's the link to the site on Wikipedia. I explain this in detail. So I will show you here. It's the Wikipedia page explaining atomic radius. It does a good job of putting this complex issue into a certain perspective. Essentially, for the purpose of this class, the understanding about atomic radius is the radius from the nucleus, the core, the center of the atom, to the outer edges of the electron cloud. So in essence, we can use the valence shell, the location of the valence shell electrons, to approximate that. So you can read through this page at your leisure, and I already provide you with the link to this page. So going back to the PowerPoint presentation, and it's also when people start to use X-ray diffraction, also sometimes called X-ray crystallography, to measure the atomic mass very, very accurately. So now we actually want to turn your attention to this dynamic periodic table. It's located on the ptable.com, and now I want you to click on the tab of properties. Click on the tab of properties. As you can see, the physical properties are listed here. We can actually click on any of those elements, and we can have this atomic radius, the value indicated here. The PM stands for picometer. 1 picometer equals 10 to the negative 12th meter. That's about a trillionth of a meter. So you can see carbon 67 picometers, silicon is 111 picometers. Those are the data we can take, actually put into Excel and start to do the plotting, because we are visual, and doing the plotting can really visualize the data and help us to identify the trend. So those are the this is the plot for group 1 elements. You can see group 1 elements have hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, and atomic number is 1 through 87. The radius is going from 53 picometers all the way up to 291 picometers for cesium. The value for francium is not available because francium is too unstable to have the atomic radius accurately measured. So now we're plotting the atomic radius in picometer against the atomic number. So this one, number 1, will be hydrogen, and this one will be lithium, this one will be sodium, potassium, rubidium, cesium. And now you can see the trend is increasing. The trend is increasing. We can actually plot, use the same approach, get the data to plot the other groups. As we can see, for the group 2 elements, we have the same trend. Group 15 elements, same trend. Group 18 elements, same trend. And you can actually do the exercise by grabbing the atomic radius data from the interactive periodic table P table and plot them. So it's easier after plotting all this. You can say, we find the trend. This atomic radius increases down the same group or family, as we can see from the hydrogen all the way down to cesium, from helium to radon, up to the second to the last element for the noble gases. Okay, so that's the general trend. Also, we can actually reorganize the data. We reorganize the data in a fashion we can actually start plotting across the period. So this is first period, second period, third period, and the fourth period. And each one of them, we start with the lowest atomic number for that period and start progressively going higher. And this one clearly is showing you another trend. And as the atomic number increases across the same period, the atomic radius actually decreases, as indicated of pair 4 elements, pair 3 elements, pair 2 elements, and pair 1 elements. So it is nice if we can actually have those type of trends being observed. But those are just a quick plotting of the actual data. The trends, then, we really have to memorize at this stage. And later on we're going to learn there are other trends going to come in. It's going to be becoming very messy. So the key thing is actually understand what are the primary factors determine the size of the element atoms. So that each time we can analyze the problem, apply the same protocol to make the judgment which ion, which atom is larger compared to the other. So I would like to say I would divide this protocol into 3 effects. Effect number 1, it states like increasing number of principal energy levels increases the atomic radius due to the shielding effects. So I'd like to explain to you what do I mean by that. And let's quickly take a look at the group 1. Let's take a look at the hydrogen. And if you draw the hydrogen circular plot, you're going to have +1 and have 1 electron on it. So generally it's pretty hard to draw this electron. Let me keep on trying. There we go. And now we can see what will be lithium. Now we can have 3 electron now. 2 rings. 2 electron on the first ring, 1 electron on the second ring. Let's continue going, and let's take a look at sodium now. Sodium now will be +11. And now you can see 8 of them in the second one. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Hold on for a second. 1, 2, 3, 4, 5, 6, 7, and that's 8. I don't want to miss one of them, and 1 here. And this kind of argument, actually, if you're drawing on paper, is becoming obvious. As the number of rings, the principal energy level increases, the number, the radius starts to increase. So in actuality, there's what we call it a shielding effect. This is what we call it a shielding effect. What actually happens here is, if we're focusing on the valence electrons, the outermost electrons, if you can see here, this electron have a direct interaction with the +1 nucleus, very strong attraction, so they achieve equilibrium at distance. So this is the atomic radius for hydrogen. However, and as you see here, the charge on the nucleus increased to +3. You got two more protons in there. However, this outermost electron is not going to feel +3 in here. The reason why for that, those two electrons are situated right between the +3 charged nucleus and this outermost shell electrons. So this electron is going to feel the nuclear charge. It's going to be shielded. It's going to be screened by those two negatively charged electrons. So roughly it's a little bit over +1 this electron is going to feel. So this electron is going to feel the attraction much weaker than these two inner ones. The two inner ones do feel the +3, and they're actually closer to the nucleus. And remember the Schrodinger's model, it dictates the first ring you can only have 2, then you have to move out to the second ring. So the size increases as a consequence. Same argument, if you have a +11 in the middle, this 2 will be much closer to the nucleus because this increased nuclear charge, increased the number of protons. This 8 is not going to feel the +11, but fairly strong, it'll be close. But this one is going to be feel much less than +11. So then that's going to be moving further away. And it is important, just let's repeat, with the increasing number of principal energy levels, that is the best indicated by the circular plot. The size increases significantly. The second effect is actually common one, actually make a lot more sense. As for instance, you increase the one from +1 to +2 to +3, and the list goes on. Now the number of protons in the nucleus, the positive charge in the nucleus increases accordingly, and the attraction between the nucleus and the electrons becoming stronger. As they become stronger, the size is going to be pulled in. The outermost shell electrons is going to be pulled in, and because it's got a stronger attraction. So as is stated here, increasing number of protons in the nucleus decreases in atomic radius, just because of the increasing in attraction between the nucleus, positively charged nucleus and negatively charged electrons. And the third effect is increasing number of valence electrons slightly increases atomic radius. This is a bit more challenging to explain, but let me do my best. So if we have a positively charged nucleus, in this case if we say if we can see +6, and now you have 1, 2, valence shell, principal energy levels, you have 2 on the inner one, 4, 2, 3, 4 on the outermost valence shell. So this is actually, we'll call it the valence shell. Okay, so on the valence shell we have roughly 4 electrons, 2, 3, 4. And don't forget, what will be the charge for each one? E minus, E minus, E minus, and E minus. What will be the interaction between those? Those green arrows just drawing for visualization. Because those 4 are still, both of them negatively charged, so electrons repel each other. So what they want to minimize the repulsion, so they want to minimize repulsion by maximizing distance between them. Okay, and now we're looking at if we have to add an electron to this valence shell. If you have to add one, you have to bring another electron in. Okay, so the repulsion between those electrons increases. How to minimize that? The solution will be just to enlarge the solution for that is just to enlarge the ring a little bit. So if I can draw it, if I can illustrate it here, if we can enlarge the ring a little bit, we can actually that's 1, 2, 3, 4, 5. We increase the distance, and actually not distance between them, we maintain the same distance between them, the optimum distance to handle the electron to electron repulsion. So in order to accommodate additional electrons coming onto the shell, coming on the principal energy level, we have to enlarge the principal energy level, the ring, slightly. So here comes the qualifier, it's just slightly. So now let's just review a little bit. Effect number 1, we increase the number of principal energy level, increase the number of rings, we significantly increase the size, we increase the nuclear charge in the middle, we're going to make the radius smaller because of the stronger attraction. So now we're looking at the third one. If we increase the number of valence electrons, if we have to put additional electron or additional electrons on the same principal energy level, we have to enlarge the shell slightly, hence increasing the atomic radius slightly. So now we actually have a protocol now. And as we discussed before, the effect number 1, number of principal energy levels, dominates greater than effect number 2, the number of protons in the nucleus, and is going to dominate number 3, the number of valence electrons. So any of this effects, if they coexist, if they present at the same time, you're going to have effect number 1 overriding, dominating effect number 2 is dominating effect number 1 and number 3. Okay, so here comes the procedure of solving any problems regarding ranking of atomic radius, or trying to find the trend of the atomic radius. You carefully analyze the problem and you generate the circular plots based on ground state electron configuration for the elements in question. And third, you identify the effects. You either be effect number 1, effect number 2, or effect number 3. And which one or which ones are present. And then you combine those effects to see which one is going to be the dominating factor to determine the size of the atom, Oop, this is a typo. Radius. Okay, so let's put this into practice then. For examples, let's take a look at, as we mentioned earlier in this discussion, the trend for the SAM group. As you go down the group, which means increasing in the atomic number, the radius goes up. So now I'm trying to understand that, and we go back to the group 1 argument. So for hydrogen, you're going to have +1 dot. If you have lithium, you have +3, 2 circles, 1 dot. You have sodium, you have +11, 3 circles, 2 dots, 1, 2, 3, 4, 5, 6, 7, 8 dots, and 1 dot. So do we have effect number 1? The answer is definitely yes. Do we have effect number 2? So let's go back to effect number 1. For 1 ring, 2 rings, 3 rings. So the number of rings increases. Effect number 2, yes, because it's a +1, +3, +11. So effect number 3, the answer is no, because on the valence shell you always have 1. They're identical. So effect number 2 will make it the radius smaller, but effect number 1 will make it much bigger. Okay? So the net effect is what's being observed. Is atomic radius from top to the bottom increases. Top to the bottom increases. Because number of principal energy increases, it's going to dominate the increasing in the nuclear charge. Let's take a look at the other trend we discussed before across the period. Actually, atomic radius goes down. I'd like to understand why. If we take a look at sodium, magnesium, aluminum, silicon, phosphorus, and sulfur, chlorine, and argon. You start to write the circular plot. +11, 1, 2, 3, and I'm going to save me some time because those two will always have 8. This one has 1 valence electron on it. This one's going to have 2 electrons on it, and aluminum is going to be +13, 1, 2, 3. This one's going to have 3 electrons on it. I'm going to very generalize it. Argon will be +18, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. And as I said before, I'm actually saving me some time. I'm now going to draw this to all the time. So those 2 rings are identical. So then in this case, do we have effect number 1? The answer is no, because all of them have 3 rings. Do we have effect number 2? The answer is yes, because 11, 12, 13 we have increasing in number of protons in the nucleus. Do we have effect number 3? The answer is also yes, because we have 1 valence electron, 2, 3, 4, 5, 6, until all the way to 8. But this one's going to make the radius smaller. This one's going to make the radius slightly bigger, because effect number 2 is going to overwhelm number 3. So the radius decreases as the result. Let's give you another example. Let's take a look at what happened to sodium. Remember, at the octet root, sodium is going to lose an electron to get a more stable sodium ion. And you will say, which one's bigger? I say, right now, I don't know. Get a circular plot. Sodium will be what? Plus 11, 2, 3. 1 here, 8 here, 2, 3, 4, 5, 6, 7, 8. And 2 more here. What would be the sodium plus? Because it lost the electron. It's still plus 11, but now I only have 2 rings now. 3, 4, 5, 6, 7, 8. So now we can compare effect number 1. Yes, this is 3, this is 2. Effect number 2. The answer is no. Effect number 3. Yes, because this is 8, this is 1. But 1 is going to... that is just not very kind writing. Not very good writing. So the effect number 1 going to dominate effect number 3. In this case, sodium is much bigger than sodium ion. Okay? One more example. Let's take a look at the one we're going from the chlorine. Remember the octet rule? Chlorine goes from the chlorine to chloride by gaining electron. Now for, say, circular plot, plus 17, 3 rings, 7 here, 2, 3, 4, 5, 6, 7, 8 in here, 2, 3, 4, 5, 6, 7, 8, and the 2 here. The gaining electron, now you'll have 18 electrons. Still 17 doesn't change. Remember, for now the chemistry, the nucleus does not get touched. Okay, so then this is 1, 2, and 3. 2 here, 8 here, 3, 4, 5, 6, 7, 8, and also 8 now. 1, 2, 3, 4, 5, 6, 7, 8 electron. Is effect number 1 here? No. Both of them have 3 rings. Is effect number 2 here? No, because the nuclear charge, the plus 17, never changed. Is effect number 3 here? The answer is yes. Now you have 8 valence electron. This one has 7 valence electron. Remember, as the valence electron increases, the size increases slightly. So in this case, chlorine atom is slightly smaller than chloride ion. Okay, so with that, and trying to recap what have been discussed here, from the measured atomic radius, we observe the trends for the same group or same family. From the top to the bottom, atomic radius increases significantly. For the same period, from left to the right, with the increasing atomic number, the size decreases, atomic radius decreases. Now we're looking at the explanation for that. We have 3 effects. Effect number 1 is the number of principal energy levels. More you have, larger the size. Effect number 2 is the number of protons in the nucleus. Higher the number, stronger attraction forces, smaller the atom will get. And this third, the last one, is as we pile on more and more electrons on the same valence shell, you're going to enlarge the size of the atom slightly due to the effort of trying to minimize the repulsion between the same negatively charged electrons. So for all the situations, you analyze the problem in detail, then you identify which effects are present. It is always the effect number 1 will be overwhelming effect number 2 will overwhelming effect number 3. So you have to do the detailed analysis and make that correct judgment in terms of comparing the atomic radius of elements. With that, wrap up this discussion and make sure you do plenty of exercises. Thank you very much for your attention.